this is really, as you can see, this one is about the why. This is a critical part, and we touched on some of it in the introduction, but I'm going to go through it again because I think it's very important that we understand why do we need to try and do this work in your country. Understanding the technical components is not enough. So what is that modern geospatial reference system going to enable you to do that you can't already do? What are the components that you need to upgrade within your country, and what priorities do you have in order to do that? And then how can you go through that process of explaining that to policymakers? And I have a couple of examples to share with you on how this has been done in other countries. I won't go through this again in detail because I touched on it at the start, and I'll slowly introduce aspects of it as we go. But if you look at that whole integration picture, the purpose of modernizing that is because it enables a few things in your country. First of all, accurate positioning and navigation. It allows you to then be working in real time with the satellite data, as I mentioned before. That's the critical thing that you're trying to achieve. Making that connection between real-time satellite information and decision-making for you or for the government or for a user as easy as possible. That's the advantage of a modern geospatial reference system. It improves data integration and consistency. Your data can't be any more accurate than your datum. And I had this discussion with someone at the Africa's workshop, and they were talking about their datum was only accurate to 0.5 of a metre, so half a metre. So what that means is that they had a datum in their country that doesn't actually allow them to implement accurate land management or cadastral land governance procedures for land ownership. If your datum is that inaccurate, you can't get property boundaries done correctly and in an authoritative way. So that shows that was a good idea for them to say that's the argument they could make to government to then modernise their datum. These are the kinds of things you've got to think about. What is it in your country that would have that impact? So you need to understand what you currently have and what the big use cases are in your country in the future. Once you then have a geospatial reference system that's in the modern format, how can you then move your old data from the old datum into the new datum? That historical data is extremely valuable. So there's some steps that we take through this week talking about how you can transform your data from the old into the new. A newer version also allows things like better spatial analysis, things like GIS software that a lot of you would have used. That is reliant on having the spatial analysis tools in the software are reliant on you having an accurate datum in which you're working. And as I said, real-time usage of that data. You would have seen a picture similar to that as shown on the right before. The bit that was not in there was that ground layer. I always like to put that positioning geodesy aspect at the bottom. Because if you have that accurate framework on the ground, all these layers of data, whether it be roads, railways, environmental information, census information, can all be built on top in an accurate and reliable way. So that accurate and reliable geospatial reference system in your country opens up a whole range of better decisions for surveying, mapping and navigation, civil engineering applications, agriculture, construction, mining, location-based services, goes on and on. And it's that geospatial reference system, all the datums, all the transformation parameters, all the guidance material, that's the glue that allows you to link all these things together and help policymakers make these better decisions. Here's an example. So what you can see here is we have our positioning layer on the bottom. If you look on the right-hand side, and you can see that we have a, let's assume that cross is a fire engine. That fire engine has a GPS tag on it. So back at the base, they know that that fire unit is travelling at 75 kilometres per hour on that road, and you have your road data, and you have your Earth observation data sitting underneath it. It's showing you up-to-date imagery of where a bushfire is. And the red component that's a bit dull is showing where the fire used to be, And then the fire front is the bright red component in the northern part of that image. So we have GPS information about the fire truck. We have our roads layer. We have our houses shown in yellow. And this allows you to do real-time decision making because all of the data is in the same datum. But what if you're in a situation like this, where you have your houses, your cadastral layer, stored in one datum, and you have real-time GPS information. It's not actually lined up with the road networks here. And then you have Earth observation imagery, which is coming from satellites, and that's sitting in a different datum. You can't actually do the decision-making you need in real time to try and help people or direct people who are dealing with an emergency. So these kind of examples can be used. They're very simple examples, but to try and explain to a policymaker that data doesn't naturally always come stacked on top of each other. There's work that needs to be done from a geodetic side to make sure that all that data is lined up and it's accurate and reliable. And a lot of that is taken for granted. So you can use stories like this to show that there is work that needs to be done underneath this in order for you to make decisions. We're going to have a look at the static component, and as I said, I'm interested here really just to get a show of hands of who is looking to do this or is partway through this process of moving from an old static datum to a new static datum. Who considers that to be something that they're working on at the moment? That's a priority. Okay, good. It's about a third. Okay, that's good. That's good to know that that's an active thing at the moment. Yes. Okay. Can you use your microphone and tell us a bit about why?
Well, we deliberately not moving data from the old system to the new system. We do connect to the International Terrestrial Reference Frame, but we keep the data in the old coordinate reference system because we don't want to bother the end users with changing coordinate reference systems.
And which country is this from, sorry?
This is the Netherlands, the European part, but also the Caribbean islands.
Okay. Okay. And
so we wait and see. If all the other countries move to the international system, then we might follow later. But for the moment, we don't want to bother our end users with coordinates which are completely different suddenly.
So can you give me an example of where this is helping the user? I think that would be good to better understand.
So this is mainly in European Netherlands. There's a lot of, almost all data is all in the same old national coordinate reference system. It's in meters, very small distortions because we're a small country. So it's very easy for users to use that. And if we try to introduce something new, in the beginning it would only create confusion and errors. So we only want to do that when we're really sure, when we move to something new, that we'll keep that for at least 50 years, or better even 100 years. And with the current status of ETRS 89 in Europe, I don't believe this is the moment to move.
Okay, so the example in Europe I can understand because you're talking about, and that's very different to some of the other countries though, because in Europe you're already using a datum which is linked with ITRF. So it's within centimeters to decimeters of what you're getting in real time ITRF.
No, our national system is on an old ellipsoid, and it's 100 meters off, which is actually quite convenient because if someone forgets to do the transformation, you immediately see it because all your coordinates are 100 meters to the north. So if I see a difference of 100 meters to the north, I immediately know what's the problem is. So I like to have this large difference instead of a small difference, because if then people don't do the transformation, I cannot see it because it's only a few centimeters or a few decimeters.
So how do the users collect information if they're collecting information in the field, there must be software or standards that are made available that then moves that back into the old datum, is that correct?
Yes, yes indeed. So all the surveying equipment producers, they supply the transformation in the equipment already. So the surveyors are using this for 25 years now. The GIS community only followed a few years ago, so we now have the official transformation in the EPSG database and also in ArcGIS and QGIS.
Okay, thanks for explaining. It shows that, so this is a great example of where the country in the case Netherlands here has done the technical work to allow the user to be abstracted from the complexities of the geodesy. And so they've done all the technical steps and put the standards in place to allow them to then take real-time data and then transition back to an old datum. And it avoids having to do that communication and the change management exercise that comes with trying to transition to a new datum and the explanation that comes with that. So I completely understand where you're coming from, and that you're right, that is the most challenging part. And you need to have a really strong business case and support in order to go through that change. So thanks for that example, that's great. So part of what we're going to talk about this week, just following on from what you just said there, that here's a great example of where it may be even more complex than this, but you've done the mapping to go from what you would get from ITRF to transform back to a static datum that users have. And that can be done using a 7-parameter transformation, and we'll explain what that is later on. Or sometimes you need a more complicated deformation model or a distortion model. And there's plenty of examples that I'd like to hear from people about this week around how they've done that in their country or in parts of their country where there's particular use cases where you need a more complex or complicated way of changing between your two datums. Because a 7-parameter transformation assumes that all the change is consistent across the country. In some cases where you have deformation or you have subsidence or you have mining, the deformation might not be consistent. So you need to develop a particular model for that region that allows you to move between different datums. Put your hand up if you use time-dependent data and you know it. All right, so put your hand up high, and then I'm going to ask a follow-up question. Now, also put your hand up if you use data from GPS in WGS84. Yeah, so anyone who went only the second time, next time you can put your hand up the first time, because WGS84 is also a time-dependent datum. If you record information in WGS84 one year, and you come back the next year and you observe it again in WGS84, the same survey mark, you'll notice that the coordinate has changed. It's because WGS84 gives you time-dependent coordinates. I mentioned before that Australia implemented both. One of the biggest challenges and complexities associated with people using WGS84 is that it's a time-dependent datum. It's always giving you the most up-to-date coordinates based on where the land is. It's not a static datum that's transforming back to a common epoch, as we heard about before. So there's this misconception about WGS84 being static and the coordinates never changing. That's not true. So it's something to keep in mind, particularly for countries who keep collecting new data in WGS84. It's always important to reference it back to some common epoch. You can't just keep recording it over time, because you'll end up having these different data sets which have different time epochs associated with it. And here's an example of the sort of the scale of that change over time. The bit that I mentioned before was Australia, which is kind of in the middle of this diagram. And you can see that Australia is moving at about 7 centimetres per year. So you imagine if you had owned a property and you had your coordinates shifting over time. That's a bit disconcerting. It's a bit scary for homeowners. So we like to have a static datum, particularly for cadastral. But then there's other systems like intelligent transport networks, as I said. Whereas if we didn't have a time-dependent datum and people are using GPS information coming through to keep their cars on the road, if we didn't update it, every couple of years, cars would start to move into the wrong lane or onto the wrong side of the road. So you need to make available different datums depending on what your user requirements are. And a lot of what we're talking about over the first few days is you understanding what you have now and what your user requirements for your countries are in the future, and then you decide what technical decision to make. And we heard a great example of that before. There's been a choice that's been made to not adopt or not come up with a new national datum because they think the country's not ready for it. That's a decision that's been made. The worst thing you can do is not make a decision, but you've got to understand why you've made that decision. That's the critical part. We'll come back to the height stuff a bit later on. I just want to keep working through some of this other information. Standards and software. It's a bit boring sometimes. It's a bit boring. But the reality is this is where you shine. This is your opportunity to do great work, because if you do this right, if you get the standards right, you get your technical models right, and you get it implemented in the software correctly, then it works for the user. The people who know less about geodesy than you, everything works for them if you get the standards in place. That's why that's so critical. And we spend a bit of time this week looking at the things that you can be doing to make sure that your datums are correctly aligned with the information in things like the EPSG register or the ISO geodetic register to make the lives of your users a lot easier. Laws and regulations. Following on from that governance discussion we have around the importance of building these national working groups or national committees, we then look at what laws or regulations need to be in place to make sure that these things are followed, to make sure that things like cadastre, underground services and aviation sector are being addressed, and that you're listening to their concerns when you're talking about changing datums or updating models in your country. And importantly, people. We need to have that discussion about capacity. We did a listening tour when I first started in this job, and one of the overwhelming things that we heard was that it wasn't just the developed countries that were having trouble getting the capacity and the people to work on this or to get trained in this. We're hearing about it in developing and developed countries. So it is a global issue. It's also important to realize that upgrading your Geospatial Reference System is not a new idea. This has been happening for centuries. The process of changing always comes down to, when do I need to update my datum because the user requirements have changed? The reason should always be based on the needs of your stakeholders. Otherwise, it's very hard to make an argument as to why you're going to government to ask money to invest in a multi-year program of work to update your reference system. And it changed for a number of reasons, whether it's scientific exploration, the mapping of boundaries, military applications, or when satellite positioning came in. Satellite positioning was the big one. A lot of countries were operating fine, working locally within their region with a local geode model, a local height datum, a local ellipsoid that fitted really well across their country. All their data sets lined up, it worked very well. But then with the advent of GPS coming in, people wanted to modernize. They wanted to make sure that their datum and their data was aligned with what was coming from satellites in real time, Earth observation data. But it always has to come back to your users, and we'll be thinking about a lot about that this week. Here's an example of how this was done in Australia. And there was a discussion that needed to happen in Australia, as I said, because the Australian plate moves so fast, and we didn't want to lose track or lose connection with ITRF and things like GPS positioning. So there was an initiative to develop a new datum and get a new positioning system for Australia. And the way that was described to politicians was to say that we wanted an integrated national positioning capability to accelerate the adoption and development of location-based technology and applications in Australia. So with those pictures and that wording, where do you see geodesy, reference system, geoid? It's not there, right? And it's deliberately not there because they don't care about that. What they care about is accelerating the adoption development of location-based technology, and an integrated capability. These are the things politicians care about. And the examples that we presented to them were things like the need to have a new datum for things like intelligent transport services. There were great use cases about having improved positioning technology in remote parts of Australia to make sure that we could have particularly small aircraft like this be able to land in remote areas where people needed health services. So there's a Royal Flying Doctors Service that come in and land in areas where there's only small or dirt runways. We needed to make sure that we had the positioning technology to allow those small aircraft to come and land in those parts of Australia that previously they couldn't get access to. And that provided improved health outcomes for Australians. Understanding the improvements in advanced rail networks. Construction, how do we improve personal safety and do aerial surveys? In this case, they were talking about having virtual fencing. So they have these little vibrating components in the backs of helmets that if trucks and people get too close to each other, or a truck goes through into an area it's not meant to be, the people can get alerted by a buzzing in their helmet. That's all based on positioning technology and providing improved safety. Drone deliveries. Drones being used for agriculture and spraying to improve environmental outcomes. Livestock. This was one of the biggest ones. The senator from the part of Queensland in Australia who was one of our biggest supporters, this is what he cared about. So you've got to find out, what does your minister care about? He is from a rural agricultural community. They're interested in mining, they're interested in agriculture. And by having GPS tags on the cattle, they could understand whether the cattle were healthy or not. Very simple, but it was something that he could understand and knew was going to be of benefit to his community. So you don't know what these applications are, but you need to go and find out what are those politicians interested in? How can I message this in a way that they can understand it and see benefit? And of course, mining. There's large amounts of the mining supply chain that are now done in Australia virtually. There's someone who sits in an office, controls trucks, controls trains virtually, with autonomous vehicles travelling throughout the regions. Helping out with people who are legally blind and needing assistance. They can be guided by GPS. They can have virtual technology that provides augmented reality over the top to help them navigate in areas that they may not be familiar or need assistance. The maritime sector. There was one port in particular where we're able to demonstrate that for every 10 centimetres of underkeel clearance that we could offer to ships, it equated to $200 million a year of extra iron ore exports from Australia. These are the cost-benefit scenarios that I was talking about before. That was just at one port. In addition to that, you're providing safer navigation. There's a range of resources here that talk about this and go into that economic benefit study in more detail, just to show you, and so these are in the slides, you can click on it later, but give you some ideas about what are the kinds of things that I should be using to communicate to the politicians or ministers from my area. And you need to work out what are the things in particular that they care about and build business cases or use cases around that.